So very good afternoon to all of you. Now we have our expert, Mr. Amandeep Sharma. He is a research scholar in our department, in electrical engineering department here in NITA. He's doing his PhD work based on health monitoring of the electric motors, and it's a very interesting topic he's working on, based, and he's using virtual instrumentation software from NI for the fault diagnosis. And today he'll be giving an expert talk on introduction to the industrial drives, which is a very important part of the automation, industrial automation. We know that it is incomplete without drives, and the fault diagnosis using lab view. Over to you, sir.
Very good afternoon to all the centers and the participants of this course. I am Amandeep Sharma and I am going to deliver a talk on the industrial drives and fault diagnosis of these drives. I am working in this area since October 2013, but right now I am just having my experimental work being arranged for the data acquisition of the faulty motors. So I will first give a brief introduction about industrial drives. What are the different types of drives and motors? Those are used in industries for various applications. And after that I will discuss about the fault diagnosis methods and techniques which can be used for the detection of faults. Along with I will discuss the types and reasons of failures which are encountered in the industries basically. So first of all, what are the different types of industrial drives? Those are used in the factories or the manufacturing units. These drives can be divided into three main groups. First are the group drives, and second one is individual drives, and the last one is multi-motor drives. These are basically classified according to the advancement that is being made over the time. First of all, we have group electric drives. These are now obsolete but are rarely used in the systems. In this type of drives, we have a single motor which is used to run all the equipment of the system. Here we have a sufficient capacity of drive or motor which is connected with the shafts and belts, pulleys, etc. to all the machinery that has to be driven. But here we have some drawbacks, like there is a poor efficiency of the overall system, as well as if one or two mechanical system fails, then the whole system won't be able to work properly. So therefore these are not much used nowadays. Moreover, it is unsafe to use these type of drives, and it has many objectionable features like the wear and tear, the overburden on the motor, and the maintenance issues. So therefore the industry is shifted to the individual types of drives. So here we have a single motor which is used to drive one type of system in the whole machinery. So here we have electric motor which is an integral part of the machine and can specially be designed for that particular requirement. For example, we have pumps, we have blowers, we have fans. So we can use different types of motors for different types of applications, and each motor will be performing only the specified work for which it is being designed. So it is better than the group type of drives. And the third type of classification we can have is a multi-motor drive. This is basically used in systems which have a requirement of more complex type of motions or a requirement of more drives for particular application. For example, we have paper industry or machine which are used for metal cutting. So these will require a number of motors or movement in the machinery. So we will have a number of drives being controlled simultaneously, and these are controlled in a fashion that all the drives work in a proper manner so that the final product is being achieved. Now we can have the industrial drives components. Basically, industrial drive components can be of three types. First is the prime mover. The prime mover is the main part of the industrial drive. It is the component which is used to have the forcing function of the whole system. Then we have the motion transmitting device, which can be shaft, pulleys, etc. And the third one is the actual apparatus or the load which is being driven by the industrial drive. So the function of the each component of the industrial drive is different. So we can therefore classify the whole drive into these three important parts. So what is an electric drive? An electric drive basically means that we have the prime mover as the electric motor. Here the motor will give the force for driving the whole equipment in the machine. So we have shaft or pulleys which are transmitting the motion of the electric motor to the associated control equipment, and the combination of the drive, the control system as well as the motion transmitting elements constitutes the electric drive of the system. So electric drives have various advantages, like it can be used in different applications with different specifications of power or gears, and can be easily varied in speed as well as torque. The drive system consists of the drive as well as the load which is being driven by the industrial drive. This load as well as the other equipment along with it will constitute the electric drive system. So now the question is, what is a drive? Here we have the drive system consisting of the electric drive as well as the load. So the whole complete system having all these three components, that is the prime mover, the motion transmitting devices as well as the actual apparatus or the load, consist of a drive system. So basically, what is a drive? A drive consists of motor as well as the control circuitry which is used to start, stop, as well as the control the speed as well as the torque of the motor as per the required conditions. So different types of drives are there. We can have a fixed speed drive as well as a variable speed drive. So depending on the application, we have different types of drives for different types of motors. It is well known that the total generated capacity of a country has 50% share which is being used for driving of motors in industrial as well as home applications. So the drive system basically helps in regulation of the motor, as well as it also saves the electricity of the user. This is the general block diagram of an electric drive. We have a source here. This can be a AC source or some battery. Here we have power modulator device which can convert the AC into DC or DC source into the AC, whichever is required. Here we have the prime mover, the motor. So power modulator can increase or decrease the speed of the motor depending on the requirement which is being fed to the control unit of this drive. Here we have a sensing unit which is used to sense the torque produced as well as the speed of the motor. This is being fed to the control unit. We have input command here, so we can in real time control the speed of the motor. Now these are some of the applications of industrial drives. We have drives being used in traveling cranes. These cranes are used in industries to carry a very heavy load from one place to another place. So we can have different types of drives here. Then we have rolling mill drives, where we can have the sheet rolling machines. Then we have textile industry, paper industries. Here we can produce the different types of motions using the drives. Then we have belt conveyors for transportation of raw material from one place to another into the industrial unit. Then we have compressors, fan blowers, pumps, etc. So these all can be driven by the intelligent drives that we have. Now we have the different types of characteristics of loads. Loads can have different types of characteristics, like some of the loads are having constant torque requirement, others have the variable torque and speed. So it is essential that our drive system matches with the torque requirement of the driven unit. So therefore we will use different types of motors or drives for different types of loads. For example, for fan type of load we have the torque which is proportional to the square of the speed. So as we increase the speed of the fan, we will have the torque requirement which is proportional to the square of the speed of the fan. Then we have selection of drives. So whatever our application will be, we have to choose the drive very carefully for that application. So first of all we will see the duty, that is whether the drive requires a heavy duty or a medium or a light duty load. Then we have starting torque requirements. Some of the applications require high starting torque. Then the limitation on starting current. For example, if our motor is being connected to a supply system which is having the power limitation, so we cannot use a very high starting current requirement type of drive here. Also we have the environmental conditions which are also influencing the choice of our drive system for a particular application. For example, the atmosphere, the environment is not dry, or it is humid, or it is very explosive around the drive, so we cannot use the DC drives here, because DC drives produce spark, so it will be very dangerous for that type of environment. Then the most important part of a drive is motors. We have different types of electric motors. The motors can be classified as AC motors or DC motors. AC motors can be classified as induction as well as synchronous. Synchronous motors are constant speed motors. So we use these type of motors in drives which are requiring a very constant type of speed applications. Then we have induction motors. These can be further classified into single phase or three phase. The further classification can be squirrel cage type or round or wound rotor type. Then we have DC motors. DC motors can be classified as separately excited or self-excited. Self-excited can be further classified as series, compound or shunt. So depending on the different types of requirements, we can use these motors for our drive system. For example, the DC motors are used widely for a wide range of applications requiring quick speed reversals, and squirrel cage induction motors are rugged and low cost, so therefore they are also used very widely. However, wound rotor induction motors are used only in cases where we have high starting torque requirement, low starting current, as well as speed control for only a limited range of speed. Then we have synchronous motor. These are usually used in applications where we require a very constant speed or a very precise control on speed, but these are economical only above the 100 kilowatt ratings, and they have better efficiency in that range. Therefore we require these type of motors only in drives where we have a constant speed as well as power requirement above 100 kilowatts. Then we can compare the DC drives versus AC drives. So basically DC drives require maintenance due to use of commutator brushes, etc., whereas AC drives doesn't require these type of components. For example, squirrel cage induction motor doesn't have any commutator or brushes, so it doesn't require the maintenance at all. Now DC drives are expensive, whereas AC drives are low cost. Then we have simple power converter design in DC drives. However, in AC drives we have complex power converter design, and DC drives are less effect of harmonics. Mostly 10th harmonic is prominent in these type of drives, whereas in AC drives we have 3rd, 5th, 7th harmonics being more prominent. So if we are using a variable speed drive for our AC motors, we have these harmonics affecting the life of the machine. The DC drives are basically used by having the AC current being converted into DC. This can be done by using the rectifier circuits. So we can increase or decrease the voltage being fed to the DC motor by using the firing angle of the rectifier circuit. So DC drives are cost effective choice for medium to high power applications. These are some of the areas where we can use the DC drives. So they are having starting torque that are exceeding 150% of the normal running torque. So therefore, applications where we require high starting torque, we can use DC motors. Then we have AC drives. They can be used to control the speed of the drive system by varying the voltage by frequency ratio. So to maintain a constant relationship between voltage and frequency, we have special circuits. Then we have these drives being used in the damped, corrosive or potentially explosive environments because of the less probability of production of sparks. We can use multiple motors here with a single driving unit, and these motors require very less maintenance because of the no moving parts like brushes, commutators, so we can easily use them in inaccessible locations. Now the second part of the presentation will be comprised of the fault diagnosis of induction motors. Here we have the requirement of fault diagnosis at an early stage because the detection of fault at early stage will decrease the abrupt failure of the machine. These abrupt failures or catastrophic failures can damage the whole system, as well as it will require costly repairs as well as total machine replacement in some cases. So therefore we should try to have an early detection of fault of motors. So here we are considering only the induction motor. Why we are using induction motor here? Because it is a very widely used motor. It is reliable, robust, and requires very little maintenance. It has high efficiency and it is self-starting, doesn't require any special type of starting. So we will now see the various fault diagnosis methods for induction motors. First of all, we can see in this graph that how a fault develops in a motor or a drive system. Here on the y-axis we have the machine condition. The machine, when it is being started at the no fault condition, it is having good health. So as we start the machine, over the time we have the condition of the machine being deteriorated. Here we have the fault being start to develop at this condition. Now at this point we will observe some vibrations in the machine, like due to bearing failures or shaft misalignment, we can have vibrations being produced here. Then we have noise, then heat will be there, and if nothing is done at this stage, then we will have the emergency stop or the breakdown of the motor at this point. So we have a sufficient time here to diagnose the fault, or we can predict the fault at early stage, so that this type of failure is being avoided. So we can monitor the faults at these stages so that we can change the faulty components in the motor. So we have to follow this curve for the maintenance of machine. So maintenance can be understood as failure oriented or preventive. In failure oriented maintenance, basically we have the motor being run to the failure, that is nothing is done to avoid the abrupt or catastrophic failure of the machine. But in preventive maintenance, we will sense the vibrations or acoustic signals from the motor, so that we can actually predict that in future what type of fault the motors can have, that is whether the bearings are faulty or the rotor has some fault. So this preventive maintenance can also be divided into different types of maintenance. One is time based maintenance. In this type of maintenance, we will have a regular checkup of the machinery at designated time, like for example 1 month, after 2 months or 3 months we will examine the machine and we will see whether there is some fault or not. Another type of preventive maintenance technique is the condition based. In this type of maintenance, we will check the condition of the machine only if there is some abnormal type of activity, like if there is high vibration in the equipment, then only we will go and see the machine. However, nowadays we have predictive maintenance more used. In predictive maintenance, we have sensors being installed on the motors or drives. Those sensors will directly give us the key features of the machine, like vibration or noise or the current that is being used by the motor. So these parameters are continuously being monitored by the maintenance system, and we can have the prediction of the fault which is going to occur in the near future, so we can safely manage our maintenance activities, or we can also have a lower cost of maintenance in this type of maintenance. So these are some of the common problems those are faced by machines in industrial environments. First of all, we have the worn. Worn means over the time the bearings or the gears will worn out due to the friction between the moving parts. So this is very common problem. Another type of problem is looseness, that is at the time of installation, if some bolts are being kept loose, so those will produce some vibrations or motion in the moving parts. This motion will propagate over the time and will become severe. So therefore we have to have different types of sensors being placed here to monitor all these type of faults. Here we have misalignment fault also. So these type of faults are basically being produced at the time of installation, and there are some faults which are occurring at the time of operation of the machines, like imbalance because of some dirt or corrosion of the moving part. So the reason of fault may be any of these type of abnormal operating conditions. Now we will classify the different faults of induction motors. First we have electrical faults, which can be divided into stator fault as well as rotor fault. Stator fault can further be divided into winding faults, then winding faults or external faults, and rotor faults can be divided into the breakage or the cracks in rotor. Here we have mechanical faults also. Mechanical faults can be divided into bearing faults, gearbox failure, and we have air gap eccentricity, which can be further divided into dynamic eccentricity or the static eccentricity. So these are the various faults of the electric motor. Here we have the bearing fault. Bearing fault can be produced in the inner race, outer race, or the rolling element of the bearing. So we can have different type of classification of faults for bearings depending on the occurrence of the fault location. So here we have these faults being further divided into various categories. So over a time the various agencies has conducted surveys and they have found that the stator related faults are around 38 to 40%. Then we have bearing faults which are maximum in occurrence. It is approximately 40%. Then we have rotor related faults and other type of faults like gearbox failure or drive system failure. So these are the data being given by various agencies, IEEE or EPRI. So they have also classified the faults in four major categories: bearing faults, stator faults and rotor faults. So this is a picture showing bearing, various types of parts of bearing, and this is rotor of the induction motor. In induction motor we have different bars here. These are being short circuited at ends. So we can have a bar breakage here, or the ventilating ducts can be broken, or we can have a crack in the end ring. These are different types of stator faults like short turns or winding faults. So I have explained this, that is eccentricity can be divided into static as well as dynamic eccentricity. So here we have static eccentricity, that is the rotor is having a displacement from the central axis towards one side and it is being maintained over the rotation time. But in dynamic eccentricity we have the rotor which is having its central axis being vibrating when the motor is rotating. So there are different types of faults in induction motor. We have different diagnostic methods for these type of fault diagnosis. So we have electromagnetic field monitoring, that is flux monitoring, temperature monitoring, vibration, acoustic, or the chemical analysis of the motors. Then we have a widely used method, that is motor current signature analysis. So we will study this type of method in detail. Motor current signature analysis, as the name implies, will have the monitoring of current that is being fed to the induction motor. So in this example we have, in this diagram we have a current transformer which is installed at the supply end of the induction motor. So commonly used method is, this is very commonly used method and it is very simple and low cost. Here we have the CT which is having the current that is being fed to the motor. It is used here because the motor can be of higher rating. So current may be in several amperes. So we can step down the range of the current here for our signal conditioning or monitoring equipment. This current is being fed to the signal conditioner to remove any noise in the supply. Then we have a spectrum analyzer which is basically converting the time domain signal into the frequency domain using the FFT analysis. Here we can see the different types of frequency components, those are present in the current. So depending on the type of fault we will have different types of components here. So for example, if we have the bearing faults, then these components will be different, and for eccentricity fault we will have different types of frequency components here. These can be further analyzed to detect the type of fault in the induction motor. So what is the principle behind this method? First of all, we have disturbances occurring in the motor or the transmission system or the attached load. So these type of disturbances will affect the symmetry of the electrical motor, and this will cause the disturbances to be propagated in the form of vibrations or torque pulsation to the rotor of the motor. So this motor will vibrate or have the effect of modulation on the magnetic field that is present in the stator. So current components that are being acquired here by our spectrum analyzer or computer will have these components shown in the FFT of the or the spectrum of the signal. Now these are the various advantages of this type of method of analysis. We have online monitoring for this type of system, that is the faults can be diagnosed at the running time of motor. It doesn't require any shutdown of the motor system. Moreover, it is simpler and cheaper because we are not using any special type of sensors here. Only a CT is used to detect the current of the motor. It is easy for testing the remote or inaccessible motors present in hazardous areas like underwater motors or in the oil field. Then we have early stage fault identification, and the maintenance cost is overall maintenance cost is reduced. So therefore we will have this type of signature analysis for finding the faults in the motor. So this is our proposed experimental setup. Here we have three-phase supply being fed to the motor. This supply is being monitored by us using the current clamps and voltage. Voltage can be directly measured by using the clip type of alligator type of clips here. For monitoring the current, we will use the split core type of current transformers. It will step down the amount of current being fed to the monitoring system. So here we have monitoring. Monitoring can be done on accelerometer as well as the acoustic signals. So combined with all these type of signals, we can have a detailed analysis of the condition of the motor. So in this we can vary the load as a parameter. We can have motor run at full load, half the load, or no load. So depending on that, we will also have several factors for our monitoring or analysis purpose. So basically, what is the idea behind this experimental setup? We will first have a motor in the fully intact state, that is no fault will be in the motor. Then we will acquire all the signals from this motor and have a particular pattern that is being shown by this healthy motor. Then we will artificially create some faults, like we have stator winding fault here, that is turn to turn fault, inter-turn fault. Then we can have the bearing faults here. We can modify the bearings, we can change the bearing here, or we can have motor imbalance. Rotor can be imbalanced using this flywheel type of arrangement. So vibration signals and current signals can be acquired from this. So depending on the difference in the healthy motor and faulty motor signatures, we can have the diagnosis of the type of fault and the severity of the fault of motor. So here is the methodology being used by us. We have induction motor being run at different loading conditions, and we have the current being acquired. This current will be first given to the signal conditioning and acquisition equipment. In our case, we will use the lab view for the processing of signal. So therefore, we will require a CRIO or CDAC type of equipment here. Then after first signal conditioning, we will pre-process the signal using FFT, averaging RMS, kurtosis, etc. So here we will have key features of the motor, that is whether the vibration signals are out of range or not as per the IEEE standards. If everything is fine, then we will have the further analysis of the signal. Here we will have the algorithm, which is actually finding the fault, type of fault. Then we will have a post processor which will classify the fault, and the severity of the fault can be detected here. This is being backed by the expert knowledge base from the theory as well as the signal from the healthy motor. So along with this expert knowledge and the signal and the algorithm, here we can have the final decision that what type of fault is there in the motor and what is the severity of the fault. So here we have different types of classification techniques. We can have the different faults being created in the motor, like bearing fault, stator fault or rotor fault. Then these signals like vibration, current and magnetic flux can be fed to a signal processing unit. It will first pre-process the signal in the form of RMS or wavelet. Then we will have the algorithm being applied here to have the final fault diagnosis. Here we can use the model based approach, the neural networks or fuzzy logic, thresholding, trending, or the expert systems can be used to find the actual fault in the motor. So here we have resources in our lab, the compact trio. It is from National Instruments. Basically, compact trio is a real-time embedded processor. It is using FPGA as the controlling device. Here we can have remote monitoring as well as control of various devices using compact trio. So in this case, we will use this compact trio for acquisition of vibration, current and voltage signals. Then we have different types of modules here. This is NI9244 for acquisition of voltage. Then we have current input module, vibration input module. Then we have different motors with us. This is three-phase motors, 4-pole, 1500 RPM, 0.5 HP motor. So we have 2 or 3 these motors with us. We can have the healthy motor signature as well as faulty motor signature with us, and we can classify the various faults. So this is all I have with me. So depending on the various fault features, we can use the data for diagnosing the fault in the motor. So any center, if has any query, he or she can ask.
सेंटर्स को फोन करने के लिए बस बकना घाट 12 यूनिवर्सिटी
एक वीडियो भी दिखानी है इसमें,
पहले क्वेश्चन आंसर करने की वीडियो दिखानी
अभी ये जा रहा है ना, वीडियो दिखाया था मेरा. So now I am showing a small video on our lab setup for fault monitoring. Here we have the induction motor. It is fed by a three-phase supply. These are the ratings of motor. It is a 0.5 HP motor. Here we have a acceleration sensor, that is accelerometer. This is the compact trio. So these are different modules for vibration, current and voltage. This is the power supply of the system. So this is being connected with the computer by a LAN cable to a remote place. Here we have the programming. We can have various programming algorithms here. We can have kurtosis, mean or pre-filtering, and then we can apply the various advanced algorithms here to diagnose the actual fault of the motor. So all the signals are being fed to the computer in real time from a remote location wherever the motor is, and here we can acquire the signals and have the various parameters like average, crest factor, etc. So this is a simple setup here. Now we will have different other sensors being incorporated in this. So this is from my side. If you have any queries, you can ask.
Sir, how the neural network used for fault detection?
Basically, neural network will be used first for training the network using the healthy motor signal. You will require a lot of data from the healthy motor. This data will be used to train the neural network. Then we will have the faulty motor signal. Now we will compare the output of the network of a healthy from a healthy motor input as well as a faulty motor input. Depending on the difference, we will see the type of fault.